going to give a very brief introduction to molecular techniques, which you may hear the words PCR, real-time PCR, things like that, when you're around the medical laboratory. Now, this is something that is typically studied more with our four-year students, but we'd like to give you a brief introduction just to kind of introduce you to it so you have some ideas as to what it is they're actually doing in the molecular diagnostics area of the laboratory. So with the amplification techniques that are used, the most common is polymerase chain reaction, or PCR. This is an in vitro method that amplifies very low levels of a specific DNA sequence in a sample to higher quantities. This enzymatic process is carried out in cycles, and there are primers used to make multiple DNA copies. So here's how this works. Each repeated PCR cycle consists of DNA denaturation, where we separate the two strands of DNA. So we've got double-stranded DNA. We're going to heat it up, okay? And then we're going to have some primer annealing. We're going to have a recombination of the oligonucleotide primers with the original single-stranded DNA. Then we're going to have extension of those primed DNA sequence. So the enzyme DNA polymerase synthesizes a new complementary strand by extending those primers. So starting on the top, we've got the two strands of DNA. It's heated, okay? Primers are added to each strand. It's now going to make two strands. We're going to take those two strands, we're going to heat them again, we're going to add more primers, we're going to extend it into even more strands, and we're going to keep this process going in a cycle until we have many, many copies of this DNA. So what are the applications of this? Well, we want to amplify the DNA. We want to identify a certain target sequence to see if the DNA is there that we're looking for. And we're going to have the synthesis of a labeled antisense probe. So some modifications that are used with this are reverse transcriptase PCR, or RT-PCR sometimes it's called. And this is modified for the conversion of RNA to DNA. We have multiplex PCR. This uses numerous primers to amplify nucleic acid fragments. And we have real-time PCR. This one's really interesting. It uses fluorescent resonance energy transfer. So for example, where it used to take about 2 days for a microbiology department to tell the nursing unit that a patient has MRSA, or methicillin-resistant Staph aureus, it would take a couple days to tell them that. Now we can give them a result in about an hour and a half. It uses the same technique that you're seeing with the PCR, but it keeps testing for that certain, let's say, MRSA sequence as it's going along. Once they get a positive signal, then they're able to determine, yes, there is MRSA in that sample, and we can report it to the physician right away, rather than having to wait for it to grow on plates and things. We have some advantages. It's a faster turnaround time, smaller required sample volumes, and very increased specificity and sensitivity. DNA sequencing is now considered the gold standard, okay, even though it's a newer type of testing. We have branched DNA, which is an alternative quantitative test that uses a signal amplification instead of a target amplification. And we also have certain blotting protocols that we use. So Southern blot is used for diseases and disorders associated with a significant change in the DNA. Northern blot looks for specific sequences in RNA, and the Western blot looks specifically for proteins of interest. So like I said, we just gave you a very brief overview of the molecular diagnostics that we do in the laboratory. Hopefully, if you continue on for your 4-year degree, you're going to get a much larger dose of how that works.